Hello, I'm Mwaffo from the Weapon, Robotics and Control Engineering Department at the United States Naval Academy. Today I'm presenting our work on experiment on pause and go state estimation and control with uncertain sensor feedback. This work was done in collaboration with Jackson Skin Curie from the Department of Mechanical Engineering at the University of Colorado Boulder, Dr. Iudice and Dr. Pietro DeLellis from the Department of Electrical Engineering at the University of Naples, Federico too. Autonomous unmanned vehicles are becoming very popular in several applications. This includes humanitarian mission, surveillance and inspection mission, or exploration mission. In the literature, research on formation control have addressed the problem of achieving a desired configuration pattern, following a desired path, performing collective tasks that cannot be achieved by a single unit, or moving in constrained environment. In the future, it is believed that team of robots might be utilized in several domains. This includes agriculture with distributed sensing, combat mission in order to overwhelm the enemy, and logistics with the future of e-commerce. In this video, released in recent years by the Department of Defense, it has been demonstrated that teams of unmanned aerial vehicles could be utilized in combat operation. Most algorithms proposed for multi-agent systems are often inspired from biological systems where it has been observed self-organized and coordinated motion. So this is the case of fish, shoal, bird, flock, bees, and ants colony. In this picture, we can actually see a group of fish executing a collective maneuver in order to avoid a predation attack. Among algorithms proposed for multi-agent system, we have the leader-follower relationship, which is a very popular scheme. In this control scheme, few individual denoted leaders are believed to have a good knowledge of their environment so that they can guide other group members towards set location. In insect group, for example, this leadership has been shown to benefit the group, notably during foraging or migration. For robotic application, leader-follower relationship might be cost efficient, as only few individuals might be equipped with expensive navigation sensor. This includes LiDAR for simultaneous localization and mapping, or differential GPS. To solve for the problem of state estimation or control, we distinguish decentralized and centralized method. Decentralized methods are often preferred over centralized method, notably in case of environmental constraint or limited communication, where centralized approach would be applicable. So in decentralized approach, real-world robots have to rely on their own sensing capability. So this includes the use of proximity sensors such as ultrasonic sensor, camera, or other light-based sensor. These proximity sensors are observed to have limited range and to provide noisy data measurement. In the literature, to solve for this issue, several methods have been proposed. So these include the development of robust estimation method, nonlinear Kalman filter, or the use of multiple sensors in order to improve the accuracy of both relative and absolute localization methods. Despite these great advances, the development of appropriate strategy capable to deal with both the absence or intermittent feedback sensor measurement is still an open research question. Here, we consider a team of N mobile robots moving on a circle with angular position θi, updated after p time step with a control input UI. Our robotic system faces several challenges. First of all, due to the use of low computational power, the onboard computer can only process data after p time steps. Each robot has no means to uncover the identity of another robot. Next, the estimated distance are absolute, so meaning that a robot has no means to know whether the robot detected is placed ahead or behind. The data returned are also noisy and limited. So this can be resumed to this equation where the estimated distance equal the true distance plus a certain noise, where the noise is bounded by a constant value, delta max. RV here is the maximum sensor range, and P is the number of time steps required actually to measure and process data. And when a given robot I cannot detect any other robot, then it will return NA. To illustrate, we consider three robots, robot I, robot J, and robot L on the circle. So robot I and robot J are placed within their cone of visibility, so clearly they can detect each other. And because robot I, for example, can only return the absolute position of robot J, so we have two uncertainty intervals materialized here in blue. While robot I can not actually detect robot L, and in that case, the estimated distance will be NA. In this work, we want to find a suitable controller UI in order to achieve a epsilon self-balanced state. So clearly, we want our team of robots to be equally spaced on the circle. And the error in the formation must be less than epsilon, where epsilon is a positive constant. The relative phase distance between two robots is defined with the function which is set so that the angle return is overlap between negative pi and pi. Before we provide our state estimation and control algorithm, let's go over some useful definition. We define the relative phase distance between robot I and robot J by this quantity phi, which is actually the absolute value of the relative phase difference between robot I and robot J. Given the measure of gradient distance returned by the sensor, the relative phase distance can be actually explicitly estimated using this expression. So here we know R, which is the radius of the circle. We can then determine the uncertainty interval when robot I and J can actually detect each other, and it's given by this interval where var max here can be explicitly computed, knowing the maximum noise value, the radius of the circle, and also the maximum sensor range angular value. We also define the maximum uncertainty interval given by bar epsilon, which is equal to this interval. And using the above definition, the following relation hold. That is, the relative phase distance between two robots is always included in one of these intervals. So in case the robots are able actually to detect each other, so it will be included in epsilon ij. And when the robots are not capable to detect each other, so it will be included in bar epsilon. Our multi-level control strategy is defined so that a leader is randomly elected. We set its control input to a constant reference value, omega ref. So leader will always move at a constant angular speed after p time step. While for all follower, that is for all robots with index I greater or equal to 2, the multi-level control strategy is defined so that initially when they are not able to detect a robot approaching, then their control input will be 0, so they will stay immobile. And as soon as they detect a robot approaching, there are two eventualities. So if the robot is placed at the desired spacing distance, then they will move at a constant angular velocity omega f. While if the spacing distance is not the desired one, then it will accelerate at an angular speed omega f plus c, where c is a positive constant. We note that in this expression, so ki here defines the first time instant where a robot is actually capable to detect a robot approaching. Now, to better illustrate our state estimation and control, we provide this figure where we have three robots: robot I minus 1, and robot I plus 1. So at the beginning of the experiment, so the robot cannot actually see each other. So in that case, so robot I minus 1 will be in the red area, so that the interval estimate of robot I, of the position of robot I minus 1 and I plus 1, will be the union of negative bar epsilon and the positive bar epsilon, as shown here. Now, when robot I minus 1 move and get into the cone of visibility of robot I, in that case, robot I will set to the empty the interval estimate for all other robots except for robot I minus 1 that it can detect. And in that case, it will actually evaluate this intersection. That is the intersection between the interval estimate obtained at the previous time step and the union between the negative interval estimate where the robot I minus 1 might be and the positive interval estimate epsilon ij. And I recall that this process is recursive and the robot will execute it multiple times, and the goal here is to reduce the uncertainty in the interval estimate gamma ij. So at the end, so you have only two possibilities: either gamma ij equal to the empty set, or it reduced to a single point, and that single point will be actually the estimate of the angular position of robot I minus 1. So for the proof, our control scheme is a particular case of a more general control strategy introduced in Iudice and all in Automatica 2020. Now, let's give some important feature of our algorithm before showing the experimental result. First of all, we note that the control parameter C can be carefully selected in order to balance the trade-off between accuracy and convergence speed. So clearly, smaller value of C might actually help improve the accuracy of our control scheme while increasing the convergence time. Larger value of C might reduce the convergence time while impacting on the accuracy of the control scheme. We know that for larger team size, our control scheme still converge, but the main problem with large team size is that pair of robots can actually detect each other, and this might actually hinder a key feature of our algorithm where we assume that at steady state pair of robots cannot detect each other. We also note that our algorithm can also converge when few agents are removed from the formation, and the only requirement here is that the number of robots remaining in the formation is updated. We note also that as leader is randomly elected, a fault affecting leader is not critical to achieve the self-balancing state. We utilize a custom-made robotic platform equipped with an ultrasonic sensor mounted on a servo in order to rotate ahead and backward to measure proximity distance. The robotic platform is also equipped with 2 plates in order to improve the probability of detection. The functional block diagram shows the Raspberry Pi computer board connected to the ultrasonic sensor. Here you utilize also an Arduino microcontroller in order to process analog data. At the beginning of the experiment, the robots are placed so that they cannot detect each other. We set a threshold of 1 meter so that data detected above 1 meter are actually trashed by our code. Initially, the first robot placed at the extremity, shown here, is selected as the leader. The robot moves at a constant speed, and when it comes close to the proximity of the second robot, that triggers the state estimation and control algorithm of the second robot, which then starts moving. After a few time steps, when waiting enter the cone of visibility of the next robot, then it triggers the state estimation and control of the third robot, which also start moving. Both robot 2 and robot 3 accelerate at an angular speed of omega ref plus c. This process will repeat itself until the desired self-balanced state is reached, and at that time both robot 2 and 3 will move at a constant angular speed omega ref. In this slide, we present the convergence of our control scheme by plotting the angular speed over time and also the phase angle difference over time. First, for the angular speed, we observe a discrepancy between the control input and the observed value due to noise into the implementation of our control scheme. Our robot implement a line follow, that is, its motion is not smooth, so explaining the discrepancy between the control input and observed value. We recall that the control input take 2 values, either 0.1 for the leader or when the robot reach steady state, or 0.3 when robot 2 and 3 accelerate in order to reach steady state. So we have the time trace of the phase angle difference between robot 2 and 1 and robot 3 and 2. We observe that the system reached the self-balancing state after about 17 iterations. In the table below, we present some statistics of the convergence of the control scheme. We observe that in most cases, that is over the 5 trials that we have performed, robot 2 will actually take a minimum of 6 iterations and a maximum of 7 iterations in order to converge, while robot 3 will actually converge in a minimum of 11 iterations and a maximum of 14 iterations. The average spacing angle between robot 2 and robot 1 is observed to be 2.02, corresponding to the desired spacing value, while the spacing value between robot 3 and robot 2 is about 2.20. Here we present the standard error 0.15 for the convergence between robot 2 and robot 1, and 0.24 for the convergence angle between robot 3 and robot 2. So in general, we observe a maximum error of 0.29 in both cases. In this slide, we present few data recorded during the experiment. At the beginning of the experiment, as we see before, the robots are placed so that they cannot detect each other, explaining why we have NA everywhere. But we note here that we have a false reading, and that false reading comes from the student that was placed too close to the experimental arena. Apart from that, we observe that most data returned by the ultrasonic sensor are NE. This can be explained by two reasons. The robot were far more than 1 meter, or the ultrasonic sensor was not able to detect the presence of a nearby robot. In this work, thus, using very few data, our state estimation and control is able actually to converge. We have proposed a non-cooperative and fully decentralized state estimation and control algorithm that has been implemented in terms of pause and go move, where during the pause, the robot stops in order to measure and process data, and during the go, they either accelerate in order to reach the desired spacing angle, or they move at constant speed when they have already reached the desired spacing angle. The proposed algorithm is inspired by the behavior of some insects such as locust nymph that has been observed to stop in order to enhance the effectiveness of their next move. The algorithms have been tested on a low-cost robotic platform equipped by an ultrasonic sensor and a low-cost computational board. We have shown that the state estimation and control strategy is capable to autonomously place the robot along the circle. Our proposed strategy is also robust enough to handle occasional false reading and other inaccuracy of the ultrasonic sensor. The pause and go scheme proposed is suitable for low-cost micro-robotic platforms that are not time critical but require limited payload and accuracy. In the future, the proposed scheme might be tested using more accurate sensor and also more powerful computational board. To end my presentation, I would like to thank the United States Naval Academy through the Volcano Fund, the University of Colorado Boulder through the Research and Engineering Center for Unmanned Vehicle, the University of Naples, Federico through the Program Star 2018 and the Project Across. Thank you. Question?